Hey everyone, we are looking at difference quotients and one definition of a derivative. So first of all, the phrase difference quotient. Difference means subtract. You knew that. Quotients divide. So it's a subtracty, dividey thing. This leads us to our definition of a derivative. So you see this subtracty, dividey thing? That is a difference quotient. There's a difference, another difference, and a quotient. This probably looks familiar. Change in y over change in x. Oh, that's slope. That's because the derivative gives you the slope. And specifically in this case, so far you've only done derivatives with an estimate of doing like a slope from 3 to 3.01 and then saying close enough. What this does is instead of going 3 to 3.01, it's going from 3 to 3, essentially. It's just bringing those points closer and closer and closer together until they're all the way close. That's what that x approaching c. So if you tried to plug c and you have f of c minus f of c over c minus c, 0 over 0, that indeterminate form. But if you could do that, the answer you get and the limit, the result of that, gives you the precise 100% accurate slope at x equals c. This bit of notation, you see that little apostrophe, like f single apostrophe parentheses c. You say f prime of c. So looking at our example, if we want f prime of negative 4, I have a thing that's saying that, what we say, f prime of negative 4. So we're going to find the slope at x equals negative 4. And just one reminder, a derivative is a limit. Whenever you're using this definition of a derivative at a point, you're going to be using limit notation because we have a limit to get that derivative. So let's see this in action. We have this parabola here. We're looking at the slope at negative 4. So to find f prime of negative 4, we want the limit as x approaches negative 4 of f of x minus f of negative 4 divided by x minus negative 4. Now, f of negative 4 is negative 10, so I can plug that in. While I'm at it, I'm going to plug my f of x in as well, this x squared plus 6x minus 2. So I still have my limit notation because I haven't taken the limit yet. And then x squared plus 6x minus 2, and then minus negative 10 divided by x minus negative 4, or x plus 4. Cleaning this up a little bit, we have our limit as x approaches negative 4. That's still there because we haven't taken the limit yet. And then we have x squared plus 6x plus 10 over x plus 4. That's not a 10, it's an 8. It's Monday. Now, if you plug negative 4 into this, you would get 0 over 0, that indeterminate form. So we need to find another way to go. Now that numerator is factorable, so I'm going to factor. I get x plus 2 times x plus 4 over x plus 4. And then looking at that, it's like, oh wait, those x plus 4s can cancel, so really we can just look at the limit as x approaches negative 4 for x plus 2. So we get negative 4 plus 2 when we plug in that negative 4. Notice I dropped my limit notation. Oh shoot, I'm off the page. Notice I've dropped my limit notation because I took the limit. So f prime of negative 4 is negative 2. And the meaning of this is that the slope at x equals negative 4 is negative 2. Okay, the next thing we're going to do is write the equation of the tangent line. We use point slope form to do this because since we have the point, if we have the slope, we have the point f of 4 equals negative 10 from way back at the beginning of this. This is going to be faster and easier than slope-intercept form. You can use slope-intercept form. This is just going to be faster because all we have to do is plug in our slope, plug in our point, x minus negative 4, and then plus our y1, so plus negative 10, and that's it. I could clean that up. I don't have to. I can just leave it exactly like this. And then the next thing we should do on this is graph our original function, graph our tangent line, and verify that we have a tangent line at x equals -4. Okay, so I have my original equation in my y1. I have my tangent line in y2. I've already set a good window for it. So we can look at this and we can see, looking at this, it looks like we have a tangent line. If I hit trace and go to -4, so y1, I have -10 for y. If I arrow down to y2, I still have -10. And if we want to, we can hit zoom and go to 2, zoom in, and I'm on -4 already. And if I hit hit enter, it zooms in and redraws things. You want to do that with the little blinky thing right on the spot you're interested in, because notice that's in the middle of the screen. But now looking at that, we can see that, yeah, this does really look like a tangent line. So to summarize what we do, here's our definition of our derivative at a point. And to use this, we plug in our f of x equation, we plug in our f of c, we plug in our c, and then we find the limit, usually by factoring. And then, if necessary, you find the equation of the tangent line using point-slope form, and then you can check it by graphing. One thing to note, being able to find the limit by factoring, that's a bit artificial. Like if I had picked a different value for x than -4, things would not have worked so nicely. So these problems are a little artificial. I mean, technically, like that limit's always true. This is always a true statement, but you might not be able to solve it algebraically. You might have to just say, look at the graph of it and zoom in, or use trace and verify it that way.